Hello everybody. So what we're going to be looking at today are the divergence and integral tests. So they're actually pretty easy to do. The divergence test is very easy to do, and the integral test is easy conceptually. However, deriving the integral test is a little bit more work, even though you don't really need it for anything. So what I'm going to go ahead and do is I'm going to start by giving you the idea of the integral test. So here's the idea. Consider an integral. Oh, I need a pen to write with. Consider the integral. Why is that uppercase? It's just an integral. Consider the integral from 1 to infinity of, let's just say, 1 over x squared dx. Okay, so what is that? Well, on a graph from 1 to infinity, the graph looks like this. We know that. And this is y equals 1 over x squared. And if we're integrating it from 1 to infinity, you could put 1 on here somewhere. Let's put 1 right here. Label these actually. Okay, so if I want this, then that integral that I did is represented by an area. So let's draw the area on here. Oops, not like that. So, you know, I'm trying to draw it, but it's not perfect. Okay, good enough. You get the idea, right? That's the area for the integral from 1 to infinity. Okay? And here's the thing, though. I can see that this is actually very closely related to two different series. To two different series. Which series? Well, let's draw one on here. So let me draw some rectangles. So actually I want to copy this. The drawing's so pretty that I want to save it. Duplicate. Move this down here. Okay. So let's take this graph and I'm going to draw some rectangles on it. So I'm going to draw this rectangle. Oh, hold on. I'm going to duplicate it again. I didn't put it like centered. Okay, there we go. Now I'm going to draw some rectangles. So if I draw some rectangles on the graph, like this, are you kidding me? Oh, it doesn't like that, I remember. Okay. So the idea is I just drew some rectangles. They have their own area. And if you calculate the area of the rectangles is going to be as follows. So the first rectangle has a width of 1 and a height of 1 over 1 squared. The second rectangle here, the height is when you plug a 2 into the function. So the height is 1 over 2 squared, and the width is still 1. The third one has a height of 1 over 3 squared, and the width is 1, and so on, right? So the rectangles have this area. Um, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus dot dot dot. Okay, and that's because the width of each one is 1, and you can just add up the area, and that's what you get. But you can clearly see that the rectangles are above the curve, right? But the rectangles are above the curve. So specifically, the integral from 1 to infinity of, what is it, 1 over x squared dx, that's actually going to be a little bit less than the sum from n equals 1 to infinity of 1 over n squared, right? Because the rectangles are above the curve. Oh, ooh, wait. The rectangles are above the curve, he said. So there we go. Inequality goes that way. So that's fine. Now, what I want to do is I want to do this again. Same thing. Duplicate this. Come on, down here. Put this somewhere. Okay. Now I'm going to draw some rectangles on this graph. So I'm going to draw different rectangles. I'm going to draw this rectangle. And of course, this time, what the difference is, right, is that the rectangles are going to be below the curve. So the area of these rectangles, what is it? Well, we have to figure it out, right? The width is still 1. Those are 1s. 1, 1, 1. The width of each rectangle is 1, and the height, like this one, is 1 over 2 squared. This height is 1 over 3 squared. This height is 1 over 4 squared. It's mostly the same as the previous one, but if you add up these areas, it's 1 over 2 squared plus 1 over 3 squared plus dot dot dot. Well, I can clearly see, well, this is also, what is this? This is a summation from 2 to infinity of 1 over n squared, isn't it? It is. So the rectangles are smaller than the integral. So I can get this, that the this from 2 to infinity of 1 over n squared, well, it's less than the integral from 1 to infinity of 1 over n squared, but that's less than the summation of 1 to infinity of 1 over n squared. Okay? And basically, the idea here is simply that this integral here in the middle is so closely related to the sums that you have on the left and on the right that if the integral converges, then the series should converge. Oh, sorry, hold on. You can't see it, but Siri opened itself. All right, so I'm not going to prove that any further, but I'm just going to make a statement here. The idea behind the integral test is this. So the sums there, one of those two sums is smaller than the integral. You can't actually say which one in general. Actually, I think you can, but yeah, you can. One of the sums is smaller than the integral. The one on the left there is smaller than the integral. So if the integral is a finite number, to a finite number, right? So you add up an infinite integral, you get a finite number. And then the idea is that the summation is smaller than the integral. So if the summation is a finite number, then if the integral is a finite number and the summation is smaller, then the summation must also be a finite number. That's the idea. Then the sum, this one, well, I'll just say the sum must also converge to a finite number because of how closely they are related. And that's not like a real proof of the theorem or anything, but that's the idea, okay? And so what you actually need is a little bit more. So I believe the integral test actually is this. Sorry. Integral test. So you start with the series, right? You're given your series, 1 to infinity, of an, given. So if you have certain things that you need, first of all, an needs to be positive. I'll say that up here actually, where an greater than, not greater than or equal, yeah, no, greater than or equal to 0. All right. If, what do we want? So what we need is that there needs to be a function, fn is a function where, first of all, f of n needs to be an. What that is that's just saying they're the same formula, right? So like, back up, sorry. The integral was this, right? Sorry about that. So the integral here, squared. The idea is that 1 over x squared is the integral if the sum is 1 over n squared, right? So 1 over x squared, 1 over n squared, same formula. So that's what you're saying here. When you say f of n equals an, that just means, you know, same formula, really. But that's not enough. You need f of n to be an for all n. For all n. You also need f of x to be continuous. Technically, it also needs to be positive, but we already said that an is positive. I'll just say it's positive here anyway. Positive, and f of x needs to be decreasing. Now, technically, it just needs to be decreasing eventually, and that's going to kind of happen all on its own anyway, but it's generally written here. So it's continuous, it's decreasing, and positive. Continuous, decreasing, positive. All right? Then, if, why is that uppercase? If the integral of f of x dx converges, then the sum from 1 to infinity of an converges. All right. Now, so that's your integral test. Now, something you might be thinking about or maybe noticed was back up here, technically it was this sum that came up smaller, right? So if the integral is finite, like let's say you do the integral and let's say the integral is 3. Well, if the integral there is 3, then you know that this one must be, you know, less than 3. That makes sense. But this one over here could be bigger than 3. So maybe it's infinity, right? Maybe it's infinity if it's bigger than 3. But that logic doesn't actually make sense because if the integral is 3, right? Sorry, yeah, if the integral is 3 and this one over here converges, right? So this one is less than 3. And the only difference between the term over here on this side, how do I do this? This, yeah. The only difference between this one and this one is that this has one extra term, right? This has n equals 1, this has n equals 2. That's the only difference. So it's not, if this one's finite, this one just has one extra number added onto it. So if you're not adding infinity, then this is not infinity. So if this one over here converges, then this one over here must also converge. Even though it's bigger than the integral, it can't be infinity. It's just bigger than the integral. Okay? So that's the idea here. And so really the moral of the story is if the integral converges, then the series converges. All right. Now, how do you do this? Well, you do it probably exactly how you think. You're just going to do an integral for every series you want to test. So let's say this. Blah, blah, blah. Continue. All right, so here's an example of an integral test problem. Oops. They say use the integral test, first of all. So that's how you know to use it. Determine if the series converges. Also, you got a 50-50 shot if you just guess, right? No, don't guess. You'll be there forever, right? Well, not forever, but you'll be there for a while. All right, so there you go. Now, typically, you're not going to do too much work to show that this meets the requirements of the integral test. You can. Like, here's what you would do. You would say, all right, so what's our function, first of all? F of x needs to be x squared over 2 plus x cubed, right? Same formula, just with x. That's your f, okay? Now, this is continuous. We can just see f of x is going to be positive as long as x is positive. If x is greater than or equal to 1. Remember, I said up here that the function should be positive, but this is going to be for, x greater than 1, right? Because that's where the series starts. Technically, you don't even need that, but, this is how we usually write it. So f of x is positive. Sure, it's positive. Is it decreasing? Yeah, it's going to be decreasing, right? The bottom's got an x cubed. It's not going to decrease at first, but then maybe it will be decreasing eventually. So f of x will decrease eventually. That's going to be good enough, because of the x cubed on the bottom versus the x squared on the top. All right. I think it's continuous. Right, so you can see I'm not really taking these that seriously. I'm just saying, okay, well, yeah, it's a function. It's positive. It's going to go to 0, I think. It's decreasing. Okay, sure. Let's do the integral. So mostly you get to doing the integral. So evaluate the integral. We're going to go 1 to infinity of x squared over 2 plus x cubed. So that's just an integral. So you do the integral however you do integrals. So like technically you should write it as a limit as b goes to infinity, 1 to b, x squared over 2 plus x cubed dx. All right, I'm going to work across the page to save space. This needs a u sub. U is 2 plus x cubed. Du is 3x squared dx. So x squared dx is du over 3. So my integral is going to become limit as b goes to infinity, integral. Top is du over 3. Bottom is u. I should change my limits, which is a little bit tricky with the infinity, but if I plug x equals 1, so this is changing the limits here, x equals 1, that's the bottom limit, implies that u is 2 plus 1 cubed, which is 3. So the bottom limit's 3. And the top limit technically was infinity, right? So u would be 2 plus infinity cubed, which is infinity. So I can still just keep a b here and have b go to infinity, and that's fine. All right, so that's my integral. Let's keep going. Gonna be lazy here. There's a 1/3 that I can take out, right? Because of that, 1/3. So it's 1/3 ln absolute value u from 3 to b. So it's 1/3 ln absolute value of b minus 1/3 ln of 3. And then we let b go to infinity. And when we let b go to infinity, we get a natural log of infinity there. But natural log of infinity is infinity. So I actually just get infinity minus 1/3 ln 3, which is infinity. So what's that mean? Number one, it means the integral diverges. But if the integral diverges, the series also diverges, which I didn't say up there when I wrote the integral test, I realize now. So let's go back and write it. So if the integral converges, then the series converges. If the integral diverges, then the sum diverges. Okay? And again, you can get that same thing from this idea. If this is infinity, then this integral, or sorry, this series is bigger than infinity, so it must also be infinity. So it's not just that when the integral converges, the series converges. It's also if the integral diverges, the series diverges. Because one of the sums we wrote is smaller than the integral and one is bigger than the integral. So you can get both convergence and divergence depending on which one you look at. All right, so that's it. Integral diverges, series diverges. Done. All right, and that's the basic integral test. So, you know, they make you do this. Sum, oops, go back, submit. Oh, okay. Sorry. I was reading something on the computer. So that's the integral test in a nutshell. You can do, you know, any kind of integral, any kind of sum that would give you an integral that you can do. You can probably apply this to. So let's do a couple more. Oh, here's one. Oh, that's terrible. We're not doing that one. All right, let's try this. Let's see. Determine if summation, we'll go 1 to infinity. It doesn't have to be 1 to infinity, 2 over 4 to the 2n converges. Right? It does. It's a geometric series, by the way, but we can still do it with the integral test. So what would the integral be? What would the function be? So the function would be f of x would be 2 over 4 to the 2x, right? Which you could probably write this way, 2 times 4 to the 2x, like that, negative 2x. So that would be the integral that you have to do. And then, again, I'm not going to make a big deal out of it. I'm just going to say, yeah, that's continuous. It is decreasing, right, eventually, because the denominator is going to go to infinity. So I'm just going to say continuous, decreasing, it's positive, etc. Those things that you technically are supposed to have. Continuous, decreasing, positive. So we're good. So do the integral. Try the integral. So you have the integral from 1 to infinity of 2 times 4 to the negative 2x dx. All right. So how would we do this? Well, we're going to need to rewrite it, of course. Limit as b goes to infinity because it's improper. b 2 times 4 to the negative 2x, like that, dx, of course. What else are we going to do? I can do that antiderivative. Maybe you have to remember here. How do you do the antiderivative of like a to the x? Remember, it's a to the x over ln a plus c. And also, if you want to combine that with this idea a to the bx, technically you should do a u substitution there, u equals bx, but I don't want to. So what would the answer be? It'd be it'd be a to the bx over b ln a plus c. The u substitution would just add that b in the denominator. Okay, and I'm going to be lazy and I'm just going to use that without doing any kind of substitution here. So I'm just going to say that this is going to be the limit as b goes to infinity. Let's try to write our antiderivative. So we got the 2 that's just hanging around. Then it would be 4 to the negative 2x over the b, which is negative 2. That's times. And then ln a, which would be ln 4. Okay. So that's from 1 to b. Like that. I just happen to notice that there's a 2 and a 2 to cancel. So we keep going. I've got a limit as b goes to infinity of, so I just have a negative. I have negative 4 to the negative 2b over ln 4 minus, I put in a 1, negative 4 to the negative 2 times 1 over ln 4. So I think I get this. This is also negative 1 over ln 4 times 4 to the 2b. Think of it that way. And then plus 1 over ln 4 times 4 to the 2, which is 16. But we don't care really. All right, now let b go to infinity. When b goes to infinity, this is going to go to 0, right? Because you're dividing by infinity. 4 to the infinity is infinity. So this is going to be 0. And this one is just whatever it is, ln 4 times 16. So 16 ln 4. Point is, the integral converges. You don't care about the number, you just care that there is a number. Integral converges. What's that mean? It means that, what does it mean? The integral converges, that means that the series converges as well. All right. So you see how to do the integral test. You just replace your integral with, you replace your series with an integral and you do the integral instead. And your conclusion is if the integral converges, the series converges. If the integral diverges, the series diverges. And that's pretty much it for the integral test. There is something I need a formula from the notes, which I don't have, so 1 second and we'll get it. There's like an error formula that we want. So I want to write it exactly right, of course. You probably will appreciate that. Continuous decreasing, blah, blah, blah. P series, we haven't done P series yet. Remainder theorem, that is what I want. That is what I want. Okay. Well, that's useless. I need the PDF. Give me the PDF, guys. Where's our book? Sorry. I'll write it. We can write it. Okay. Actually, before we do the remainder theorem, what I want to do is I want to talk about P series first. So let's do that. Let's do P series. P series. No, not Siri. Go away. Oh. No, go away. Okay. Oh. Okay. What's a P series? So a P series is this kind of series. Is this 1 to infinity of 1 over n to the p. Okay, that's a P series. Now, using the integral test, which I'm not going to do because we've already done 2 integral test examples, we don't need a third, but using the integral test, you can show that P series converge if P is greater than 1, and they diverge if P is less than or equal to 1. Okay, now again, you can show that, you just have to do the integrals. But I don't want to do the integrals. How would you use this? So the idea is, if I just write a couple down, let's even change the numbers here because they don't matter. 1 over n to the pi. 1 over n to the 0.99. 1 to the infinity of 1 over what? Square root n, right? Which converge. Right? And the idea is you don't have to do the integral test. You could do the integral test on any of these, but you don't need to. You don't need the integral test, even though it works. It does work if you do it. It does work. What you need is just to identify the P, and then you'll know the answer. So like on the first one is P equals pi. That's bigger than 1, right? Larger than 1, converges. Easy. The next one, P is 0.99. That's 1 or smaller. I mean, it's smaller, but 1 is the cutoff point. 1 is smaller, diverges. What about the last one? It's a square root, but a square root, remember, is a power of 1/2. Now, it's actually n to the negative 1/2, but we're not considering the negative power because we're already considering a fraction. So I'm only looking at the power in the denominator, not as a negative exponent. So P is 1/2, which is 1 or smaller. Diverges. And it's as easy as that, okay? Just figure out what the P is, and then you should be able to say converge, diverge, whichever one it is, okay? So that is going to be pretty straightforward. All right, so let us now talk about the remainder theorem, which I could not get from the, what's it called, webpage with the book. Had to get it from the actual PDF. Okay, so here's the idea. So let me get this picture back. This one. I like that picture. Duplicate. Now head down south with it. All right. So what are we doing? We are going to look at the remainder theorem. remainder theorem for integral test. Okay, so the question that we have is this. So what are we, like, why are we even doing this? What's a remainder? What are we even talking about? So the idea is this. So suppose you want this value here. So suppose you want the value of some series. So let's just say we're looking at this series. So we're looking at the series 1 over n squared, right? Which looks a lot like the integral of 1 over x squared. So suppose you want the value of that integral, and it goes from 1 to infinity. That's a sum, not an integral. But suppose you want the value of the sum from 1 over n squared from 1 to infinity. Okay? Now you can't calculate the whole sum. You don't know how. So what are you going to do? Well, what you could do is just say, well, the terms are getting smaller as you go. So what if I just add up 5 terms? Right? What if I just say this? What if we just add up I was going to say we, but what if you just add up the first 5 terms of the sum? It's not the whole sum, but maybe it's pretty close. Maybe that's close to the full sum. Why would it be close to the full sum? The reason it would be close to the full sum is because the terms get smaller and smaller as you go. So the ones at the beginning are more important than the ones at the end. So maybe you just add up the first 5, right? Now, if you add up the first 5, you'd be calculating what we call S5, right? S5, the 5th partial sum. So let's just say this. So we say, what would we say? S5 is approximately this thing. Okay, now it wouldn't be perfect, but it would be close. But the question we have is, how far off would we be? Okay, and it turns out that, so we say that, how far off could this be? Well, if you go back to the inequality that we had at the beginning here, oh, I thought I lost the inequality. So if you look at this inequality here, right, then you've got this integral sandwiched between 2 sums, okay? I'm not going to derive it, but you could also technically have a sum that was sandwiched between 2 integrals. I'm not going to write it, so I apologize. The moral of the story is, because of how closely the integral is related to the sum, you could say that S5 well, the full sum, 1 to infinity of an is stuck between 2 things. So the full sum is going to be stuck, like if we add up these terms, actually those are the wrong ones. Let me draw them. So we're adding up the first 5, right? Is that what we decided? Yeah. Okay, so we're just adding up these first 5, and that's what we're going to use for our sum. Now, basically, the part that we didn't calculate is over here. So if this is our estimate, can't even spell estimate. If this is our estimate, then everything that we didn't add up over here is the error. right? Because we're stopping after 5. We're adding up 5 terms, and then everything else that we didn't add that we were supposed to add is error, because it's supposed to be there and we didn't calculate it. Well, we don't know exactly what the error is, but the error could be related to the integral, right? Like, what if you did the integral from 1 to 6 of 1 over x squared dx? That would be this area, right? Under the curve. Now, isn't that going to be approximately equal to the terms of the sum that we didn't calculate? It would be. It would be. So when you're trying to calculate the full sum, it turns out that it's in between the first 5 terms. I'm writing this with 5, but we can do it with any. So it's stuck between S5 plus a certain integral. In this case, it would be 5 to infinity. And another integral, the integral would be 6 to infinity. And that's what it's stuck between. And so what you can do is you can say, well, what's the error then? The error would be if you define the remainder, what we call the remainder, that's why I'm giving you a name, the remainder, Rn to be, what is it? This. Rn equals sum from 1 to infinity of an minus Sn. So if you take what we have here, then what you can do is you can show, I'm not, but you can show that Rn is stuck between Sn, no, sorry, the integral from, come on, into infinity of f of x dx, and the integral from n plus 1 to infinity of f of x dx. Basically what you would do is you would come here, and if you just subtracted S5 from all 3 sides, then you would have your S5 in the middle but not on the edges, and then it would look like this, but with a 5 instead of an N. And this should be a capital N too. All right, so that was terrible. Here's the moral of the story. I'll write out the actual theorem. So suppose this AN is convergent. I guess I better start it at 1. Is convergent, positive terms. And F has all the properties that we normally need. So we need F is continuous. F is decreasing. F of n equals an for all n greater than 1. We define the partial sums. We already know that, but I'm just going to say it. Sn is, n equals 1 to capital N of an. Then finally, Rn, called the remainder estimate, or error. So the remainder estimate, or error, is given by Rn between integral from n to infinity f of x dx integral from n plus 1 to infinity f of x dx. Okay? And so that's how you do it. And so you actually have to calculate two integrals. They're almost the same integral, right? The only difference is the bottom thing. So it's not going to kill you to calculate, but that's what you have to calculate. So let's do one, only one, because of how long they take. Because you have to do two integrals just to do one. All right. Well, we're going to actually have to do more than one. Let's try this. Example. I can't use that example. That example's dumb. Okay, well, give me a good example. Give me a good example. Well, I give up. No good examples, only bad examples. So let's try this. If you use, if you estimate integral, I'm going to say 1/2 to the 3. Oh, that doesn't make sense. 1/2 to the n from 1 to infinity. I can't write things that make sense today. 1 to infinity. If you estimate this sum from 1 to infinity with S5, how far off might our estimate be? All right. And basically what you have to do is just calculate those two integrals and you'll figure it out. So we know that R5, I'm not going to, say it's decreasing and all that, but I know that R5 is going to be between the integral from 5 to infinity of 1/2 to the x dx, and also greater than or equal to 1 to infinity of 1/2 x to the 6th. 1/2 x from 6 to infinity. So you have those two integrals there. And so all you have to do is calculate them and see which one, whichever one is bigger is going to be the one that is the error. Okay? The biggest out of those two. So compute them. So calculate the integrals. Okay, I'm going to cheat. I'm going to do it real fast. Hopefully. Let's do this. 5 to infinity, 1/2 x dx equals. All right, limit as b goes to infinity. We're going 5 to b. What's the antiderivative of 1/2 to the x? It is, what is it? It is 1/2 to the x over ln 1/2. Okay, so there you go. Put in your b, put in your 5. Limit as b goes to infinity of 1/2 to the b over ln 1/2 minus 1/2 to the 5 over ln 1/2. B goes to infinity. 1/2 to the infinity is 0. And then so I just have minus 1/2 to the 5th, which is 1 over 32, over ln 1/2, which, if I grab a calculator, actually turns out to be positive, or it should. So 1 over 32 divide by ln 0.5, and so I get 0.04508 ... Okay, now if you do the other integral, the integral from 6 to infinity of 1/2, x dx. Everything's going to be the same, right? Except that you have a 6 instead of a 5. So I'm going to jump straight to here. So you have a 6 to b. That's hard to tell them apart. 6 on bottom, b on top. So you have a limit as b goes to infinity of 1/2 to the x over ln 1/2 minus 1/2 to the 1 over, wait, no, 1/2 to the 6 over ln 1/2. So you do that integral, and it's going to come up almost the same, but it's going to be 1 over 64 over ln 1/2. So it's going to be literally half the size of the other one. Right? So those are my two values. Like the remainder has to be between those two values. So actually, yeah. So I know. So we know the remainder, R5, satisfies R5 between 0.04508. We know it's less than that, but we know it's bigger than 0.02254. So it's stuck between those two values. So we know we have at least this much error, and we know we have at most this much error if we use the first five terms of the series to approximate our error. Okay? So that's how you could do that. It boils down to just literally setting up those two integrals on the left and to the right and doing them. That's easy or hard depending on whether the integrals are easy or hard. Now, that's not a question that they actually ask you, though. They ask you these weird ones on the homework, and so I'll find one and we'll do it. We will find it. Come on. I know we will. Just give me one. I guess I can get one from the book. Okay. Oh, they do ask one of these. That's nice. All right. Yeah, they do ask one of these, and they want the number. They want the number that I highlighted in orange. Is what they ask for. All right. So here's another type of question, though. They say, find the minimum in such that the SN estimate of the sum 3 to the n to the 6 is accurate to within 0.001. All right. Now, so just so we're on the same page, right? What we're saying here is this. You could approximate the sum as, you could say, oh, well, let's just add up the first 5 terms. That gives me a number. You could say, add up the first 10 terms. If you add up 10 terms, your estimate for the full sum is going to be better, right? Like, so we know, like S10 estimates the sum, better than like S7, for example. right? Why is that true? Because we're supposed to be adding up from 1 to infinity. So 1 to 10 is better than 1 to 7, right? If you're supposed to be going from 1 to infinity. So we know that. We also know that the way you measure how close it is with the remainder. The maximum error comes from the remainder. Now remember, the way the remainder is set up, though, you have an integral from capital N plus 1 to infinity of the f of x dx, right? And the thing is that the remainder is less than that. So the other side is what the remainder is more than. But why do we care about that? I mean, well, maybe you do care about that, but we don't care about that. If we're trying to figure out what the maximum error is, we only need to look at this side. The remainder is less than what you have on the right. Okay, so we're just going to calculate this. So what you do is you just evaluate. Oh, wait, hold on. Let me stop 1 second. They make a mistake. Oh, no, they don't. I lied. I put these on the wrong side. My bad, sorry. Sorry. I didn't do that wrong earlier, right? Sorry. No, I had it right before. Okay, so we know the remainder is less than that integral on the right. So what you're going to do, though, is they're asking for the n. They want us to calculate the n. They don't tell us. So what you do is you leave it as an n. Leave it as a variable n. Do the integral. Set it less than 0.001. Is that what they gave us for the number? Yeah, somewhere. Yeah, 001. So we want to do the integral, set it less than 0.001, and solve for n with algebra. All right, 1 second. Can't pause the video. So I apologize. To plug the thing in to the wall. All right. So calculate it. Okay. Solve for it. So that's how you do this. These are the steps. So the integral is, we need to evaluate integral from capital N to infinity of the f of x for whatever our function is. So our function was what? Where is it? Where is it? Okay, there it is. So our function is going to be, we need to do the integral from n to infinity. It was 3 over n to the 6. So 3 over x to the 6, right? So that's the integral that you do. So just do the integral. So you have to write it, formally it is improper. So n to infinity, n to b goes to infinity. Rewrite this as 3x to the negative 6. Do the integral. Should be easy, it's power rule. So 3x, add 1 to the power, divide by the power. Before I plug in the limits, I'm going to rewrite this as negative 3 over 5x to the 5. From n to b. put in your b. Put in your n, right? We're just leaving n as n, so we have to leave it that way. And then b goes to infinity. When b goes to infinity, this term becomes 0 because you're dividing by infinity, and you have simply 3 over 5n to the 5th. Okay? Now the idea is that this is your maximum error, right? So we know that Rn is less than 3 over 5n to the 5. And we want that to be less than 0.01. Right? That was given in the problem. We didn't come up with it. So all you do is you say, okay, well, we want 3 over 5n to the 5 to be less than 0.001. So you write that, and we just find the n. So just solve for n with algebra. It's not too tough. Just bring the 5n to the 5 up, or actually just the n to the 5. So 3/5 less than 0.001 n to the 5th. So n to the 5th is greater than 3/5 over 0.001. Okay, so 3/5, do that on the calculator. 3 over 5 over 0.001, you actually get a big number. You get 600. That's not that big. If you're trying to solve for n, you need to do the 5th root, or 1/5 power. So 600 to the 1/5 is 3.5944. Okay, so what that's telling you is this. This is saying if n is larger than 3.5944, then Sn will approximate the full sum, which from 1 to infinity, of an with error at most 0.001. Okay, so what n do we use? Well, you can't use 3.5. That doesn't make sense. So we'll use n equals 4 and compute S4. All right. So I am going to go now, try to answer my door, and I will talk to you guys later.